In number 24, they want us to find the density of helium gas, and they want us to express it in one of these funny ways. So you remember that the way you find the density of a gas, which is probably one of the hardest gas law problems, is you start from piv nert and you substitute the n here. And what you substitute the n with is mass divided by molar mass. So I'm going to do grams divided by the molar mass of the compound. And it's been a long time since we've looked at that, but that's what you substitute it with. Once you do that, you got to solve for density because we're trying to figure out the density. And you remember what density is it's mass divided by volume. And in this case, mass is going to be grams and volume is going to be liters. But since the symbol is V up here, we got to somehow get G over V together. Well, I've already got G on top, so I'm just going to bring the V down on the other side. So I'm going to get G divided by V. I still have my molar mass down there, and then everything else is the same. So that's my density. Then we just got to get everything else on the other side. So I'm going to bring the molar mass up over here. Oops, forgot to erase the V there. That's gone because it went to the other side. And then we're going to have to bring the RT down over here. So just doing a little bit of algebra. And this is equal to density. Alright, so we've got our equation. Now all we have to do is plug in some numbers. So to plug in some numbers, let's see. Well, they tell us it's at standard temperature and pressure. And so we know the pressure is going to be 1 atmosphere. The molar mass, if you look helium up on a periodic table, is 4. And then R, since it's a gas, is going to be 0.0821. And the temperature in Kelvin is 298. Because it's standard temperature. Now all we got to do is somehow figure out the math here. And the 4 times 1 is easy, that's 4. And then on bottom, you're going to have 0.0821 times 298. Now I'm going to approximate that as 0.1. That's going to be a little bit bigger than our number is going to be. I'm going to approximate this as 300. Because 300 times 0.1 would be 30. So it would be like 4 divided by 30. And it'd actually be a little bit less than that because you remember we did 0.08 instead of 0.1. So it'd be something a little bit less than 30, like 28 or even less than that. And you'll notice if you keep looking like that, D certainly looks an awful lot like it. 4 divided by 22.4. So I think D is going to be the correct answer. Number 25, we have an experiment where they're mixing hydrogen and oxygen. They were completely reacted, and so there's no equilibrium going on here. And it was done above the boiling point of water. I think they're saying that so that we realize it's going to be gas. According to the following equation in a sealed container of constant volume and temperature. And the question is, if the initial pressure in the container before the reaction is denoted as P sub I, which probably stands for initial, which of the following expressions gives the final pressure, assuming ideal gas behavior? So what I've done up here is I've drawn a diagram of what the flask looked like beforehand. We have the green dots represent the hydrogens, and so I drew 2 of them because 2 of these are going to react with 1 mole of oxygen, so I only drew 1 of those. And if it reacts completely, they'll both go away, and afterwards they'll be gone, and all you have is water, and according to the equation you're going to have 2 of them. So clearly, if they're all gases, the pressure in the flask beforehand is going to be higher because you have 3 moles of gases over here, and the products afterwards you only have 2 moles of gases. And you can see that from the balanced equation. So the pressure is going to be less afterwards. So that lets us rule out some things right away. Like if you look at A, the pressure is not going to be the same, it's going to be less. It rules out B because it's got to be less. It even rules out C because C is 3 divided by 2 is 1.5. So the answer has to be D, and I think it makes sense that it would be 2/3 of the pressure. So it should be D. Number 26, it looks an awful lot, almost exactly the same as the one we did before. Nitrogen gas was collected over water, and you remember whenever you collect it over water, you need to remember to subtract out the water vapor pressure. And here's our eudiometer tube again. If we collect a gas and it bubbles up through here and collects here, I'm representing the black dots as nitrogen. There's always going to be a little bit of water vapor pressure. It's not going to be much, but we're going to have to subtract it out to get the true partial pressure of nitrogen. And this might be a good idea to remind us how we write partial pressure. The partial pressure of nitrogen would look like that. And the partial pressure of nitrogen and the partial pressure of water in this should add up to the total pressure. That's Dalton's law of partial pressures. So, since we know that the total pressure was 796 millimeters of mercury, and we know the vapor pressure at this temperature was 55, then it should be pretty easy to figure out the nitrogen one. You just subtract them, and it looks like it's going to be, is that 741? Well, anyway, I'll let you subtract them and figure out what it is on this one. Number 27. An ideal gas fills a balloon at a temperature of 27 degrees and 1 atmosphere. By what factor, as in how many times, will the volume of the balloon change if the gas in the balloon is heated to 127? So clearly we're increasing the temperature, and they want to know how the volume will change if the balloon is constant. Let's think about a little bit of kinetic molecular theory while we're here. If I have gases, and you'll notice right away we need that in Kelvin. And so I've got it down here in Kelvin where we added 273 to it. So if I have a set amount of gas, and the pressure isn't going to change, if you heat them up, you remember they're going to start moving faster, and when they start moving faster, they exert pressure on the balloon. The only way it's going to stay the same is if the balloon expands. So we are expecting it to get bigger. Now, I think the whole trick to this question is if you remembered to convert them to Kelvin, it becomes a lot clearer. It's not like we're going from 27 to 127. It's not going to be a huge amount. We're increasing it by roughly a quarter, and we know that it would get bigger. So you would not want to choose 3/4 here. You would not want to choose B, because that would be getting smaller. 3/4 of something is smaller. So definitely you want to choose C here, because 400 divided by 300 is 4/3. So C is the answer. In number 28, they're wanting us to find the molar mass, the molecular mass. It's just molar mass of a gas. And they tell us a lot of information about this gas. So let's start with the definition of what molar mass is. Molar mass is grams per mole. And if we start there, if we can figure out the grams and we can figure out the moles, then we'll be done. We know that there are 10 grams because they told us there were 10 grams. We just don't know how many moles there are. And I'm going to abbreviate it as N, because that's what we tend to do with gases. Now, how do we find N, the moles? Well, we've got so much information, we might have enough stuff to figure out the moles using PivNert. And so I'm going to rearrange this. N equals PV over RT. And if we can find N, we'll plug it in down here. Let's see, the pressure is 2 atmospheres. The volume is 6 liters. The R is 0.08. And the temperature is 26 plus 273, which is 299. Okay, so we have those things. Now we're going to take all of this and plug it in down here on the bottom. So we're going to get 10 grams divided by 2, 6, divided by 0.08, and 299. And then you remember, anything that is in the denominator of a fraction that is in the denominator is really on top. So I think you're going to get 10 times 0.08 times 299 divided by 2 and divided by 6. See what answers match that. Ooh, it's looking an awful lot like A. If you don't like that rearrangement, though, you could try this. You could multiply everything in the equation on top and bottom by 0.08 and 299 to convince yourself of this. Watch this. If I multiply the top by 0.08 and 299, and I multiply the bottom by 0.08 and 299, well, this will cancel with that, and I'll still have this stuff on top, and you'll notice that we'll get this answer down here. So A should be the answer. Number 31, how many moles of sodium sulfate must be added to 500 milliliters of water to create a solution that has a 2 molar concentration? Okay, so let's start with this. One is, we are only going to have to add make a 1 molar solution of this whole thing. And the reason is because if we have a 1 molar solution of this, it's going to kick off 2 NAs. Let me show you what I mean. So when Na2SO4 dissolves, it's going to make 2 sodium ions and 1 sulfate ion. So if we want a 2 molar solution of this, we only need a 1 molar solution of that stuff. So that simplifies things a little bit. And then we remember that molarity equals moles divided by liters. We want a 1 molar solution. We want 500 mils of it, so it's going to be 0.5 liters. We just need to know how many moles to weigh out. So 1 times 0.5 is going to tell us that the number of moles is 0.5.